Amin. He is an assistant professor at Rice University in the Department of Physics and Astronomy. I have known Mustafa for a long time, since he was a Pappalardo fellow, postdoctoral fellow at MIT, which I think was from 2008 until 2011, because at that time he had the very good taste of starting to work on oscillons, which is something that I have been working for a few years before that. But before he was there, he had a PhD in physics from Stanford with Roger Blandford on the title of the thesis being Probing Gravity on Disparate Scales. And that's from there he moved to MIT. He stayed there for a few years. After the Pappalardo postdoctoral fellowship, he stayed for another year at the Center for Theoretical Physics. And then he moved to the University of Cambridge, UK, as a senior Kavli fellow, where he stayed until 2015. And from there, he moved to Rice, where he is since then, 2015. So about 5-6 years now. So it's a real pleasure to have Mustafa. I admire his work. He's worked on many different fields in astrophysics, cosmology, field theory, the mathematics of solitons. And I think what he's going to do with this smashing solitons of cosmology is somehow bring most of these things together and entertain us. He says that there are some very pretty movies, which, knowing his numerical work, I'm sure there will be. So Mustafa, welcome, and the floor is yours.
Thanks, Marcelo, for this very generous and kind introduction. And before I begin, I should say that my career certainly would have been very different had it not been for Marcelo's work. So I was fortunate to, and I'll mention how I came upon working on many of the things that I'll mention, and it is intimately linked with the work that Marcelo had pioneered. So it's a pleasure to give this colloquium. As the title says, I'm going to be talking about smashing solitons of cosmology. Cosmology, I think all of you probably know what that is. Smashing, well, that also you know. But solitons, maybe it's a word that's not familiar to everyone. So before I start my talk, let me just tell you what a soliton is. So let me start with some history, a historical context of what a soliton is. So in about 1834, our friend in this top hat here, John Scott Russell, was riding along a canal. I'm not sure he had a top hat or not, but he was certainly riding a horse apparently. And he was riding along a canal, and a barge came to a stop in this canal, and it created a pulse of water. And what Russell notes is that he watched in amazement that this pulse that was generated in the surface of water traveled without distortion for a few miles. Okay, so it was a pulse that just kept on propagating. It did not dissipate away. This, in some sense, is a soliton. Okay, or this is the first example of a soliton. What is a soliton? Well, it's a very long-lived dynamical excitation in a field where the nonlinearities of the system balance out the tendency to disperse away. Now, here, the field that we are talking about is the surface of water. In general, you can find these solitons have been found in the fields of optics, hydrodynamics, Bose-Einstein condensates, and there is certainly a lot of room for such objects to exist within high-energy physics as well as cosmology. It's these solitons in cosmology that what I want to focus on today. Having told you what a soliton is, and by the way, please interrupt me for questions if you have any. I'm happy to answer them as the talk proceeds. So that's a soliton, right? It's just a localized lump of the field that travels without distortion and hangs around for a long time. Now, I want to talk about solitons, not in any field, but for solitons in particular in cosmology. And to start it off, I'm just going to show you a bunch of movies. Okay? And the rest of the talk is just going to be me trying to explain to you what is happening in those movies. So let's start with that first movie. So this is a movie about formation of solitons. The color here represents density of some medium in the universe, and lighter regions correspond to more denser regions. And hopefully you notice that starting from a roughly homogeneous system, you form these localized dense structures. These dense structures are the solitons. Let me show you another move. Some of these lumps of energy density, okay, they form and they can interact with each other. And the interactions are quite interesting. So here are some examples of the types of interactions they can undergo. Next, when these things interact, they can give rise to some interesting signatures. Here is an example of two of these lumps of energy density colliding together and giving rise to a signature in gravitational waves. So that's something that one could potentially explore. And here's one more thing, which is very recent work, where collision of two of these lumps of energy density of solitons in cosmology could give rise to a very dramatic flash of light, which we can hope to detect. So these movies are basically what I'm going to be talking about in the colloquium to tell you, what is going on inside these movies, what's the motivation for them, and so on. For those of who have a more theoretical bent and are a bit impatient about what's going on here, let me just say that everything you've seen is based on this action. It's just a real valued scalar field with gravity, and occasionally I will couple it to the electromagnetic field. So there's not much else going on in these very rich dynamics except this. Okay, so having given you sort of my the punchline in some sense of what you're going to see throughout the talk, let me now get back into a regular mode of the talk and go through these things more slowly. So the plan for my talk is the following. I'm going to give you some motivation for why the kinds of movies and kinds of systems I considered, why we should consider them, what is their relevance to cosmology. Then I will tell you some details about the physics of what's going on, give you some intuition about why such dynamics comes about. And I'll spend the later half of the talk discussing the implications, okay, of observational implications of how we could go about looking for such dynamics. That's the plan. So let's start with some motivation. So I showed you this movie where some roughly homogeneous energy density clump together into these localized structures, which I claim are solitons. So why is this relevant? Why should we study such systems? Well, it turns out, as I will argue for you, that such dynamics could be happening very early on in the history of the universe, in the first fraction of a second of our universe's history, at the end of a period called inflation. And it could happen even after that period to some extent. Okay? The same kind of dynamics, I claim, can also happen in a very well-motivated model for dark matter called axions. And that these objects could be soliton-like structures, and these dynamics could be happening in the present-day universe as well. So these are two sort of eras in our universe where such dynamics that I showed you could be taking place. Just to put this in our context again, here is a cartoon history of our universe. So there is, I would say, evidence is consistent with the idea that very early on in the history of our universe, the universe underwent a very rapid period of exponential expansion called inflation. During this period, tiny quantum fluctuations got stretched out to humongous scales, and we see the imprint of those fluctuations in the first light that we receive, when the first atoms basically formed. This is a cosmic microwave background. This light is not perfectly uniform. It has tiny inhomogeneities in it. This is related to inhomogeneities in distribution of matter at that time. Gravity takes us over, makes things clump further. And as this clumping proceeds, and through a lot of fun astrophysical processes, we eventually get the formation of galaxies and ultimately us. So in this sort of big picture history of the universe, the dynamics that I'm referring to, this formation of solitons and so on, could be taking place in these two locations in time. One during the time when inflation ended, and also between the period between the end of inflation and the formation of first atoms. And it could also be taking place in dark matter in the present day universe. So these are the two places that you should have in mind when you think about when are these dynamics taking place. In terms of the component of the universe in which this dynamics is taking place, it could be completely separate, even though the physics will be quite similar in terms of, the mathematics will be quite similar. In terms of giving you a sense of scale, these movies that I was showing you with these lumps of energy density and so on, if this process is taking place at the end of inflation, then the scale is microscopic. It can be even subatomic. Whereas if this process is taking place and you're thinking about it in the context of dark matter, then these objects, these solitons and so on, could be quite macroscopic. And depending on parameters, could even be astrophysical in size. So it's a very broad range of scenarios in which such dynamics could be relevant. Okay. Let me dig into this a little bit further. So first I'm going to describe for you, go into a little bit more into the details of the motivation as well as the dynamics. And first, let me just study the system with a real valued scalar field. Right? A scalar field is it's a simpler version of the electromagnetic field. Instead of 3 components, it has only 1 component, and it's a scalar at each point in space, and it can evolve in time. This scalar field, the dynamics of this field is governed primarily by what is called the potential. And this potential has a shape. Again, this is a little bit technical, but it won't be completely relevant for later things, so it's okay if this, for the students, if it's not completely familiar. It's more for me to feel good that I've said what I needed to say. So this potential now has a shape. If the potential is just m squared phi squared, then we say that these particles of this field don't interact with each other apart from gravity. But if this potential has a shape like this, where it opens up away from the minimum, then you can imagine that this potential, the particles in this field have an attractive interaction in addition to gravity. That's a simple way of thinking what this potential does. Okay. Why should one consider fields with such potentials? So it turns out that when we measure the fluctuations in the light emitted from the time the first atoms formed, that is a cosmic microwave background, it tells us that if inflation was driven by a scalar field, then the shape of this potential has this opening up form. It's quadratic at the minimum, and it opens up as you move away from the minimum. So that gives us a good motivation for why we should study such potentials. Another strong reason for studying such potentials, systems with potentials that open up away from the minimum, is because, as I said before, a very popular type of dark matter called axions, which was initially came about as a solution to what is called the strong CP problem, essentially a way of describing why the neutron's electric dipole moment is tiny, unobservable at the moment. Okay. And it provides an excellent dark matter candidate, this field, and it also has a shape that opens up away from the minimum. So both of these cases give us motivation to study these systems. Okay. Right. So having said that these systems are interesting, let me just now show you a movie again of the dynamics that takes place. And it's easier to understand what's going on in 1 dimension first, and then I'll show you the results in 3 dimensions. What I'm going to show you here is the dynamics of just a single real valued scalar field in a potential like this. Okay? The field starts out homogeneous in space. In this figure, the horizontal axis is position, the vertical axis is amplitude of the field. The green line is basically the value of the field in space everywhere. Okay? It's roughly constant. I will allow now the field to evolve, and you'll see something quite interesting taking place. So it starts out almost homogeneous. But as you see, the field starts oscillating up and down. But as it starts oscillating, it doesn't stay homogeneous. It actually breaks up into these localized configurations that you saw also in the 3D movie that you saw. I want to stress that the formation of these objects here, in this scenario at least, has nothing to do with gravity. Okay? It has to do with the fact that the potential is sort of opening up away from the minimum. Let me just show the movie again. You will notice that as the field starts oscillating, there's some instability, right, that sets in that makes the field break up. So what is this instability? Why do fluctuations in the field grow? You can write down the equations of motion of the fluctuation, and you can show that because the equations of motion of the fluctuation have a term where the background oscillations of the field act like a time source, a time-dependent frequency in the system, as a result of which fluctuations can grow rapidly. This is a result of what is called Floquet theory, but you don't have to buy this technical aspect here. I can demonstrate this behavior for you with the help of my friend Paola Robusco. Okay? Hopefully, many of us have experienced this before. So if you go on a swing and you start standing up and down, then you can find that the amplitude of the swing will grow rapidly. What's going on in terms of the growth of fluctuations that I showed you, the instability is very similar to this. The oscillating field rapidly sources the fluctuations that grow, just like the amplitude of the swing here is growing. So that's the phenomena of parametric resonance that's causing the growth of fluctuations. Okay. You might say, maybe I had chosen some very specific initial conditions that led to that, that you weren't able to see. But hopefully this movie, where I'm starting with something rather random looking, if I let the system evolve, again, you see this formation of localized structures. By the way, here I should mention that it was this actually paper first. This was a paper by Farhi, Guth, Iqbal, and Graham that got me interested in this. And this paper in turn was inspired by Marcelo, I believe, giving a talk at MIT before I had arrived there. And it was based on this work that these authors here got interested in. It is because of that that I eventually got interested. So it's because of this that, again, just thanks to Marcelo, that I even got involved in this at that time. I have to say that when I first saw the results of this paper, I did not believe it when I was told about it. And so I had to go and simulate this myself to believe that such kinds of things could happen. And that's how I got interested. Okay. So hopefully I've sort of convinced you that the formation of these things is insensitive to initial conditions. And even though I showed you these movies in 1D, we have of course done this in 3 dimensions. And so have other authors, including Marcelo, and seen the formation of these objects quite easily. And it's dimension independent in terms of, as far as the formation of these objects is concerned. What are these objects? If you take, I've been talking about these solitons, but what exactly are these objects? If you take a slice through them and you look at what this field phi is doing, you will find that it's just doing something quite unusual. Okay? It's just oscillating up and down, up and down, up and down. It's a field configuration that's oscillatory in time, it's spatially localized, and it's exceptionally long-lived. The name of this configuration is oscillons, and Marcelo pioneered the study of these objects in 1990s. There is a lot of interesting thing about why these objects are long-lived, what's really going on, and I can go into detail about this if people are interested, and of course Marcelo can say more about this. But I can just say that there's a lot of evidence to show that these things can last in certain situations for many billions of their oscillations, and even hundreds of billions of their oscillations without any trouble. So they are long-lived in terms of that timescale of oscillation. So in that sense, but they're not perfectly stable. They should, in most cases, I think, should decay away eventually. But they're extremely long-lived things, and that's why we refer to them as solitons. Okay. So these oscillons that I talked about are not sort of solitons that are just something that exists in vacuum in some sense all by themselves. They're actually part of a family of such solitons. If similar configurations in the case of real valued scalar fields are what we call oscillons, they're supported by self-interactions of the field. If real valued scalar fields are held together by gravity, then they're given the name oscillaton. If you complexify the field, then those things are called boson stars. Similarly, if you take the oscillon with self-interaction and make the field complex, then these objects are called cuboids. So there's a family of such solitons that exist that people have been studying for a while. Especially in the context of such solitons held together by gravity instead of these self-interactions, there have been exciting recent work. One of the papers that I really like is this paper by Levkov et al., where they showed that even if you start in a virialized halo of axion-like dark matter, then after sufficient time, you get a nucleation of these solitonic structures inside them spontaneously. So that's quite an interesting thing as well when these things are forming basically by gravitational interactions, not by self-interactions. Okay. So far what I've told you is that it's interesting to study these objects and hopefully convince you that they form quite easily from generic initial conditions in a cosmological context. Now what I want to do is try to ask the question, sure, you form these objects, but what is sort of the long-term dynamics of the system? Well, what do these objects do once they are formed? Do they just hang around separately and expand away as the universe expands, separated away? Or do they cluster? What is going to happen? As you might imagine, if you want to understand the long-term dynamics of the system, you have to take gravity into account. However, gravity is a rather weak force, and it's going to take time for these objects to cluster. At the same time, because the field inside these objects is oscillating rapidly, that means that you have two timescales. One is the gravitational clustering timescale, which can be incredibly long. And then there's a short timescale of the oscillation, which is quite short. So if you want to numerically address this problem of clustering, it creates a huge dynamical range problem. So what you have to do is you have one way of getting around that is somehow you figure out how to integrate out the fast oscillations. And this is something that you can do in a systematic way. And what happens by doing this is that you take a relativistic system and by integrating out the fast oscillations with some care, you can convert it into a non-relativistic system. So you go from a Klein-Gordon equation, which is relativistic, to a nonlinear Schrodinger equation, which is non-relativistic, along with gravity. And you can then address questions of clustering a little bit more easily. So we did that in one of our works with Philip Marx. And the initial movies that I showed you was actually with this gravitational clustering included. Now, here are two sort of snapshots from our simulations of soliton formation, where in one case we included gravity and the other case we did not include gravity. I don't know about most of you guys, but it was certainly very difficult for us to just look at this and see if there was anything interesting that was anything different between the two. So you have to look for things a little bit more carefully. So what we did was we constructed a 2-point correlation function. That is, how likely is it to find something at a certain distance away from a given object statistically in these two scenarios, and try to see if there was any difference between them. By the way, we should look at the dynamics. It's very straightforward. It's just snapshots. It's not so clear. And when we did that, we definitely saw strong evidence of gravitational clustering of these objects. This is a bit of a busy plot, so let me walk through it. The colors here represent time. Blue is early times, red is late time. The dashed lines is a system where we ignored gravity, and the red lines, or the solid lines, are the ones where we included gravity. So you notice that at late times, which is red, you see that systems with gravity certainly develop a non-zero correlation, which is because of gravitational clustering. Another interesting bit, which is important, is that at very early times when the objects just form, there is a negative correlation, which means that objects are less clustered compared to Poisson. That's because there is a characteristic instability scale on which these objects form. That's why you see a slight negative correlation. But the shape of this correlation function is consistent with what you might expect, but the time evolution we don't fully understand yet. It's just something we are thinking about carefully. Okay, so once you include this gravitational clustering, it allows for this possibility of these objects to undergo interesting interactions. Right? They can talk to each other because they can come close to each other. And when they come close to each other, they can do some rather interesting things. This movie that you're seeing, hopefully the center of the blue circle, you saw two objects merging together. This merging of two objects is one possibility of what could happen when these solitons come close to each other. Another possibility is that these objects can bounce off each other. Now, this is somewhat surprising, at least at first glance. These objects are just made up of a collection of scalar particles. Why is it that some of these configurations bounce off of each other and some of these configurations merge with each other? Indeed, you can have even more complicated dynamics rather than just mergers or bounces. You can also have things like orbits where these objects start forming orbits around each other. By the way, these are all just extracted things from our simulations. We didn't put in by definite initial conditions. These are just things that we see in the simulations themselves.
Mustafa, can I ask a question?
Yes, please.
Is this including gravity with expansion or with just some background? What are you doing in terms of the gravitational component here?
So it includes both Newtonian gravity as well as expansion.
Okay.
So it's not strong field gravity, meaning it's not GR, but we are well within the Newtonian approximation though. So it's Newtonian gravity that allows for clustering as well as background expansion. So Marcelo, the reason you see these objects seemingly shrinking is because of the expansion because it's in co-moving coordinates. So you see the expansion of the universe here.
Okay. But they're much, much smaller than the horizon length.
Oh, absolutely. Absolutely. This is much smaller than the horizon scale here.
Right.
Thanks for that question. So I'm sorry I didn't write down the equations here, but it's essentially, it's a Schrodinger-Poisson system of equations in an expanding universe. So it's full field evolution. It's not like we are treating these solitons as point particles. It's full field evolution. It's just we have integrated out fast time scales to get the system. That's what we've done. Okay. So what is the key underlying reason why we see such interesting interactions between them? It's because along with the fact that this is a collection of particles, if you remember, the field inside these objects is oscillating, which means there is a phase associated with them. Of course, individually, the phase has no meaning in terms of what is the time when you start the phase, that's arbitrary, but you can talk about relative phase between two objects. So it could be that one oscillon is coming in with some phase like this, and other one is coming in, but the phase, they're offset in phase, or they can be in phase together. So there is another degree of freedom, which is the phase of these objects, or the relative phase of these objects. And it's dependent on this relative phase that you get this rich behavior of interactions between them. So it's not just a simple system of point particles now. Now there's, when they come close to each other, they see much more interesting behavior. We can see much more interesting behavior here. In general, if the relative phase is 0, then they end up merging together. If the relative phase is pi, then they bounce off each other. Okay. So let me, again, because there are these ingredients in the talk, I'm going to again summarize where we are so far. So I've just told you again that you can start with somewhat generic initial conditions. You can get the formation of these solitons. They can undergo gravitational clustering, and because of that, they can go some quite non-trivial interactions. Now I want to ask the question, what are the implications if such dynamics are taking place? There are two kinds of implications one could think of. What are the gravitational implications and what are the non-gravitational implications? Moreover, both gravitational and non-gravitational implications, we can talk about these in two different eras. One possibility is we can think about these dynamics taking place at the end of inflation or in the early universe, or we could think about these dynamics happening in dark matter in the late universe. If these were happening in the early universe, you could change the behavior of how the inflaton field responsible for causing inflation transfers its energy to other fields. The formation of these objects is a rather rapid and inhomogeneous process, so that could give rise to a stochastic background of high-frequency gravitational waves. Okay? This is typically higher frequency than what you can detect with LIGO. Stochastic gravitational waves could be generated by this. And potentially, although this is hard, you could form primordial black holes because these large overdensities are clumping together. So that's one set of possibilities that could happen in the early universe. There are others related to phase transitions and so on that also Marcelo has worked on that I'm not mentioning here. In the late universe, if this is phenomena we are thinking about in dark matter, then it could this formation of solitons and so on could allow us to distinguish it from other forms of dark matter, in the sense that there could be extra structure on small scales that we could look for, and these solitons and so on that we could look for. Again, these objects smashing into each other and so on in certain parameter ranges could lead to gravitational waves. And as I mentioned, in the case of dark matter, especially axionic dark matter, it could also be a source of signatures in light. If I were to talk about all of these implications in detail, it would be a rather boring and also very long colloquium, I suspect. Well, hopefully not boring, but definitely long colloquium. So I'm just going to pick two of these things to walk you through a little bit of the details of what one will see there. So first, I'm going to talk about the signatures, potential signatures in light, partly because this is some of my newest work right now with a postdoc, Zhonggang Mo, at Rice, and I think it's quite exciting. Just to again quickly remind you of some of the relevant scales. These oscillons that I'm talking about, if they're held together by self-interactions in a potential like this, there are some relevant parameters. One is the mass scale at the bottom of the potential. This is little m. And then there is a field distance capital phi, where the potential changes away from quadratic, that I'm calling capital M. In terms of these parameters, you can write down things like the radius of these solitons as well as the mass of these solitons. And here are just some typical numbers that you can use. We don't know the mass of the particle that makes up the dark matter. So we have a broad range of possibilities in terms of what the radius of these solitons can be in dark matter. So that's why there's this broad range. These could be small, tiny objects, or these could be huge objects. It just depends on what these parameters turn out to be for dark matter. And in some sense, we should look for all of them because at the moment we just don't know. Okay. So focusing on this dark matter part and flashes of light that can be generated. In this case, the action, again, for the theorists among you that I'm thinking about is a real valued scalar field in which we have these oscillons. And the natural coupling of axion-like fields comes from what is called this FF dual coupling. In terms of electric and magnetic field, it's just this field phi multiplied by E dot B, where E and B are your usual electromagnetic fields. This F squared here is E squared minus B squared. Okay, this is the usual electromagnetic Lagrangian. This is the part that's the coupling between the scalar field that forms oscillons and the electromagnetic field. The essential idea here is simple. I've argued that these objects, these oscillons, can form easily in axion-like dark matter. Now the question is, they're just hanging out by themselves. But it turns out that in some special situations where I've told you with gravity, they can come together, right? So it turns out that in some situations when they come together, okay, even though they were not emitting any light when they're hanging out by themselves, when they crash into each other, a threshold is crossed, and suddenly a significant fraction of all the rest mass energy that's included in these objects gets converted into photons, giving off a burst of light. So this is an idea through which we can potentially hope to look for these objects non-gravitationally and try to see if these connect to something we already see in the sky. This idea, by the way, this idea of axions coupled to light is not new in any way. What is interesting here, at least from our context, is sort of this happening with these oscillon-like structures, where the high density of the field and the fact that it only happens when they merge is somewhat of an exciting prospect. Okay, let me just show you this movie again that I showed you at the beginning of the colloquium. So here is in blue is basically the energy density of these solitons. Initially you will, and then I'm gonna start the movie. On the left-hand side, it's the energy density of the soliton. On the right-hand side right now, which is black, will be the energy density in the electromagnetic field. So notice that there is no emission before the merger. It's only after those objects merge, some threshold is crossed, and suddenly you have a burst of electromagnetic radiation coming out. This is a non-trivial thing actually that's going on. And so I'm going to walk you through this again a little bit. So the important elements are that as if these objects, these oscillons are hanging by themselves, the coupling to photons is still there, but the conversion is quite inefficient. Okay? The most stable configurations that I can think of for these oscillon objects initially are not in the right configuration that they can emit radiation. They just hang out by themselves. There's a threshold that's not crossed. But when they merge, a threshold is crossed and suddenly there is an explosive production of radiation. And this process is self-regulating in the sense that once you produce enough light and you've taken away enough energy away from the oscillons, again, it will settle down and not emit radiation. It will again settle down into a mostly stable configuration. In terms of some numbers, when these two oscillons merge together, we find that about 30% of their total energy goes into just scalar radiation, okay? Whereas 20% of their total rest mass energy goes into electromagnetic radiation. Now, these objects are macroscopic objects, so 20% going into electromagnetic radiation, or macroscopic in terms of the energy density, so 20% going into radiation, into electromagnetic radiation is a huge amount in this case. To give you a little bit of insight into what's actually going on, why do you get this burst? If you remember early on, we talked about this phenomena of parametric resonance. When you have some oscillating background, you can efficiently pump energy into the fields for which this background is acting as a time-dependent mass or time-dependent frequency. So even here, what's happening is when you write down the equation for the vector potential of the electromagnetic fields, the oscillon acts as an effective time-dependent mass. Now, in general, if it was homogeneous, then the axion field is homogeneous, then there's no threshold effect. It's always producing, so these objects, so this would have happened early on in the universe already. But because of this threshold effect, these objects can exist and not radiate, but only when their amplitude and radius becomes of a particular size will they end up suddenly explosively undergoing parametric resonance and producing this flash of light. So that was in some ways the new part here. So here is just a little bit of a quantitative description of what I'm saying. On the vertical axis is the luminosity in photons, on the horizontal axis is time. Pre-merger, there's just noise in the luminosity, so there's no luminosity in photons. As they start merging, you suddenly, this is a log-log scale, so you get an exponential growth in the luminosity. And once back reaction sets in, that is, you have emitted enough of the energy away in photons, they again settle back into very minimal radiation. Again, this is a log-log plot. This fact here that you see something not dropping down to these levels. It's just because we have a finite volume. So there's radiation coming back into this. Okay, I've already said the numbers, so I won't do this again, but you emit energy that's quite significant in electromagnetic radiation. The frequency is roughly corresponds to the mass of the axion, whereas the energy corresponds to both the mass of the axion and what in the case of axions we would call the decay constant as well. I've been somewhat optimistic and I haven't given you all the caveats about what this happens, but there's a lot more work that needs to be done to make this sort of, for me to tell observers that they should go look for this in terms of merger rates, collision rates, in terms of whether oscillons can last for this long. Even though oscillons are very long-lived, are they long-lived on today's cosmological timescales? That's a question that I don't actually have an answer for. Also, the strength of the coupling to electromagnetism has to be in a certain window. It's about an order of magnitude bigger than the typical QCD window. So that's something that's one has to think about more carefully. So there are lots of caveats here. So it's not a done deal that we should definitely go out and look for them, but certainly I think it's an interesting thing to pursue. One of the things that we are looking into, which for the astronomers, of course, I mean, one of the more exciting things recently is these fast radio bursts that are not completely explained, most likely. Of course, I also think that they're likely related to bursts in maybe magnetars and neutron stars and so on, or gamma ray bursts. Of course, we don't know for sure what these are, but it could be possible that some of these flashes that I'm talking about could be linked to these fast radio bursts. Again, a lot more work needs to be done before I can claim that this is a reasonable solution. Another thing we are looking at is what happens when these solitons enter a domain of strong magnetic fields around neutron stars. That's another, there's some interesting interplay between electromagnetic fields and these fields that make up the oscillons there. And potentially, if there are these electromagnetic signals coming from there, and if I can convince you that it could also be gravitational signals, we could hope to look for multi-messenger signals from these mergers. So I have about, I'm assuming, Marcelo, do I have about 5 minutes or?
You do, absolutely. Yeah, okay. Go ahead.
Good. So I have about 5 minutes or so left. So I'm gonna just quickly tell you about gravitational wave signatures and then I'll summarize. Okay. So far I've not really talked, I mean, I mentioned gravitational waves, but I've not really shown you a direct calculation. Okay. So this is, again, in some sense, a toy calculation, although it required a lot of work. What we're doing here is now because we are interested in gravitational waves, we are going to do a calculation with full generativity, but this time I'm going to ignore the self-interactions. It's just, this is the system we decided to study in 2018 first. Okay. So we're going to create really compact objects now. It's unclear how they actually form, but I'm going to take them as given for the moment and try to understand what the gravitational wave signatures would be in this case. So it turns out that there is, again, a lot of rich physics here that takes place. So if these objects are compact, but not too compact, okay, so they're around neutron star densities or neutron star compactness, a little bit fluffier than neutron stars. And if they merge together, here's the kind of signal that you see. So on the left-hand side, you are seeing the energy density of these fields again. And on the right-hand side, you will see sort of the gravitational waveform as a function of time that you might expect to see. So you notice that as they are coming together, nothing is happening, but as they merge, there's a quadrupole moment that is generated, and you see a signal in gravitational waves as these objects emerge. Notice that in this case, where their merger was in phase, they don't merge immediately and just settle down. There is a ringing that takes place. So you can look for sort of what looks like, and this word is used differently in different contexts, what looks like echoes of the initial gravitational wave signal. Okay? So this is something that could be an interesting signature to look for. So this is a template for gravitational waves one could look for with LIGO and so on. Again, not claiming that this is the final scenario, because these are, head-on collisions rather than in spirals yet, but it just gives you an indication that there are intrinsic signals hiding here. Another possibility is that if these objects are a little bit more compact than the ones that I've shown, these are now pretty close to neutron star compactness, a little bit even higher than that. In that case, what happens is that the same behavior is seen before they merge in gravitational waves. But if they are sufficiently compact, then after they merge, that it can actually collapse to black holes. Okay, so this is because this is a full numerical GR simulation, we can actually see the formation of a black hole here. So these objects can also combine together and form black holes, and this is what we have simulated here. And now I can sort of try to compare and contrast what you would see compared to what would have happened if instead of these oscillons or these, what they're now called oscillons without self-interactions really, when they merge compared to what would have happened if you had seen the signal in comparable mass black holes. So here the vertical axis is the amplitude in gravitational waves, horizontal axis is time. The black curves are what you would see from comparable mass black holes, whereas the colored curves are what you are seeing based on the collision of these solitons. So if they are somewhat fluffy, then you see these orange signal, which sort of repeats. This was the first movie that I showed. If they're critical in the sense that they merge to form a black hole, then the signal is quite similar to what you would get with black holes. However, notice that the amplitude, the colored amplitude is actually larger than that of comparable mass black holes. The reason for that, we believe, is that these objects are slightly more deformable, as a result of which there is a slightly larger quadrupole moment when they're merging, which is possibly why we get a larger signal here. And then if we did just as a cross-check, we just took these objects that were so dense that they collapsed to black holes before merger, and then the situation is identical to what you would get with just similar mass black holes. This is sort of an interesting diagram that we thought was revealing. So this on the horizontal axis is a compactness of these objects. On the vertical axis is what fraction of energy density of energy is released in gravitational waves. So you notice that there is a region here where the objects merge in from black holes, but the energy density in release in gravitational waves is actually higher than this dashed line, which corresponds to what we would get from corresponding mass black holes. So you can get some higher emission in gravitational waves from merger from these objects than you would get from corresponding mass black holes. And once they become degenerate, which means they're black holes before they merge, you again return back to the normal line. So something, again, we are thinking about more and seeing if this survives when these things happen with mergers that are in spirals, not just head-on collisions. Again, there are, of course, caveats, and you can here that you can ask me more about in terms of populations and so on and so forth. Okay, before I end the colloquium, I feel like I should mention the following, which is another thing that's I'm quite excited about, and particularly after I've come to Rice, I've been even more excited about this. So everything I've talked about so far is speculative in the sense that we haven't actually seen these configurations in cosmology yet. I think it's not unreasonable to expect them, but of course nature might just choose that that it doesn't have the right parameters for these objects to form, or maybe the models of scalar fields that I was talking about are not really chosen by nature. So it remains speculative at that end. Worth looking for, but it's speculative at the moment. We have no evidence for those things existing yet. However, there is a system where these objects, to an extent, I would say, or objects or analogs of these have been observed, and that system is basically an exciting system of Bose-Einstein condensates. So if you take the non-relativistic limit of these oscillons, they become solitons in the Schrodinger-Poisson system, and mathematically you can see a connection of how you get from this Klein-Gordon equation to this Schrodinger-Poisson equation. Now this, or rather just the nonlinear Schrodinger equation. And when you get to the nonlinear Schrodinger equation, it is well known that these objects, that this equation describes Bose-Einstein condensates really well. So it is no, so if our understanding is correct, then we should see such objects, at least the non-relativistic versions of this, in Bose-Einstein condensates. And the top panel that you are seeing is not, for once, it's not actually a simulation. This is actually real data from Bose-Einstein condensate in lithium atoms. This is from Randy Hewlett's lab at Rice. And these dense structures that you see are basically analogs of oscillons. They are solitons in nonlinear Schrodinger equation here. And you're seeing them form here, and you can also see them interact. Some of these phase-dependent things that I talked about are also visible in the interactions. So it's quite interesting and exciting to see this, and I'm trying to collaborate with them a bit more to understand what more we can do here. It's not exactly the relativistic system, but I still find it fun to sort of explore it in this context. Okay, so this is the end of my tangential digression. And let me now summarize what I've told you. So this is the visual summary. I've hopefully argued that both in the context of end of inflation and in the context of dark matter, it's reasonable to expect in many models that from generic initial conditions, you get the formation of these solitonic objects, which we call oscillons, if they're governed by self-interactions, or sometimes oscillons, or just solitons when they're, or boson stars, and so on, if they're governed by gravity. It's quite generic for these objects to form. Once they form, with the help of gravitational clustering, they can undergo some complex interactions. Both the formation as well as these complex interactions could lead to signatures that we can look for in astrophysics and cosmology. Two of the things that I focused on in the colloquium was gravitational wave signatures from the collision of these objects in today's universe. And another one I focus on is that if this is an axion-like fields, then it's possible that collisions of these objects can also generate an electromagnetic signal, a burst of electromagnetic radiation that we can hope to also probe. With that, thank you very much. Thanks.
Mustafa, thank you so much. Let me see if I can get my camera here. Yes, that was great. Thank you. I actually missed that. I'm going to clap for everybody. So you're having 40 people clapping right now for you. I missed one question that was asked by Avery, who is Robert Caldwell's grad student during the talk, which was really related to inflation. So Avery, let me see if I can, why don't you ask the question yourself instead of me reading it? Are you there?
Sure. Can you hear me?
Yeah, we do. Yes.
Excellent. Sure, absolutely. Mustafa, thanks for the talk. It was really interesting, and I learned a lot. So yeah, I was curious about, you sort of split the oscillon signatures into post-inflationary effects in the early universe, and then maybe late time effects if the scalar field describes some dark matter candidate or something. So I was curious about this post-inflationary regime, and sort of curious about the timescales involved. I think the essence of my question is, you talked about having to do this sort of, this dynamical range problem. So you have to integrate out the fast timescales of the oscillon so that you can hope to resolve the gravitational timescales, which are much longer. But I was curious if even these fast oscillon timescales are comparable to, let's say, timescale during which the inflaton might decay in a preheating scenario. So I think that's sort of the essence of my question. Is it possible that inflaton decay is going to be too rapid in these standard scenarios anyways to even hope to see oscillon dynamics? Or are the oscillon dynamics still on timescales where gravitational or otherwise you can still see some of these interesting effects?
I see. So, thanks, Avery. That's a great question. So I think the first question is that if I'm thinking about these objects at the end of inflation, could it be that couplings to other fields would just never let these oscillons form in the first place? And that's certainly a possibility. I have we don't know the couplings in the early universe to other fields in detail. So it's possible that if you couple it to very light fields, it might be possible that oscillons might never form at all, and you might get energy into other fields. So it's certainly possible, and we don't know. Right? So it could be that this whole scenario I'm describing in the early universe, maybe no oscillons form. That time scale, if the coupling, one way of estimating this is to ask, is the self-coupling of the oscillons larger or weaker than the coupling to other fields? Based on constraints that we know from Big Bang nucleosynthesis and so on, I can say that there's no reason for the couplings of the inflaton to other fields to be necessarily stronger than the self-couplings that give rise to oscillons. So it's not a statement that it has to be, but there's no observational indication that the scenario I'm describing cannot take place. So that's one answer. Now, in terms of gravitational timescales, if you're willing to, gravitational clustering will take place on many Hubble timescales at that time. And during that time scale is definitely much longer than the oscillation timescale that you're interested in. So it would be interesting to do it that way. One caveat, Avery, sorry, I'm giving a long answer to this because there are many parts of your question. One caveat to this is that if the objects that we are describing, these oscillons, integrating out fast timescales is only useful if the size of these objects is still large compared to M inverse. If the size of these objects is still very small compared to M inverse, which is the mass scale in the problem, then you don't benefit much by integrating out the fast timescale because you still have to resolve the spatial timescale as well, and relativity then forces you that you have to do both together. So only if you're talking about objects that are somehow big in size in terms of physical extent compared to the typical mass scale in the problem, but the oscillation timescale is fast, can you do this trick of integrating out the fast timescale? Does that answer your question, Avery?
Yeah, that was excellent. Thanks so much. And thanks again for the great talk.
So, Mustafa, I have a couple of questions here, but I'm going to give preference to Hans Miller because Hans Miller is the Miller in the Gleiser-Copeland-Miller paper.
I see.
Who actually was my PhD student when I started working on this. So at Dartmouth now he does interstellar plasma physics. So Hans, go for it.
Thank you, and thank you for this talk. It was wonderful to see this all come to a lot higher fruition in the intervening years. It was a pleasure to do this in the 90s, but it was really great to see so much progress. I was particularly interested in the merger of oscillons.
Right. Yes.
So I was left wondering whether or not you can actually find merger initial conditions that would actually allow the oscillons to go through each other, very similar to like a Korteweg de Vries encounter of two solitons, that they would actually re-emerge unscathed after the interaction.
Yes.
Do you think that is in principle possible, that they would actually not do a radiation event, and in fact reform?
So I can actually tell you, I mean, I didn't include this, but we have actually looked at this, and it's not similar to Korteweg de Vries in the sense that they escape unscathed unless you are talking about very low amplitude oscillons. So if the oscillons are really low amplitude, meaning they're, and then you have to be essentially in 1D for them to be stable, then they can pass through each other without any problem. However, I think a more general way of saying this is that if you want these oscillons to just pass through each other without merging, then you would have to throw them at each other at ultra-relativistic speeds. So the physics of this is that if you throw them at ultra-relativistic speeds, then the time duration over which they overlap is so short that they don't really have any way of deciding whether they should merge together or what they should do, and they just pass through each other. So
wow, that is a very fascinating answer. Thank you.
And we have done these simulations, and you see this actually happening. Hans, one just minor thing to just say that if you include gravity, this gets even more interesting because then you have to think about, okay, when you throw them at really high speeds, of course, what if they're general relativistic objects, what happens to the formation of black holes and so on? And this has also been investigated. I can talk offline about what happens in that case.
Very cool.
Excellent. And I have a question here from an anonymous attendee, actually two questions, but they're somewhat related. One is about what sort of numerical simulations you use to create the results, and whether you looked at the gravitational waveforms from oscillon in spiral as well, so that you can really compare. I'm complementing the question, so that you can really compare to black hole inspiring waveforms.
So Marcelo, these are, again, thanks Anonymous and Marcelo for these questions. So the movies that I was showing you were quite a different slew of simulations. So I can maybe...
Were you shooting them at each other head on with some relativistic speed? Is that what?
So let me just show you. So this movie right here, for example, where they were shooting at each other and I was calculating gravitational waveforms, this was perhaps the most challenging of them all because this was full numerical relativity, and the code that we were using is called GR Chombo. So this is developed by a bunch of people, in particular, one of the collaborators on this paper, Eugene Lim, as well as Thomas Helfer, Thomas Helfer is now a postdoc. Eugene was his faculty advisor. They developed this code which can do scalar fields in full numerical relativity. Okay, so that was used for these numerical relativity simulations. When I was talking about these mergers with electromagnetic radiation, this was a code that was that has a scalar field on a lattice, which along with gauge fields, and in this case we use a code which had gauge links in it. If you're familiar with what is used also in lattice QCD kind of things, because this is a gauge theory, although it was an overkill. We did not need it here at all, and indeed new simulations we can do it much more easily. So that's what we use here. The earlier ones, we just had a scalar field only. That was done using a code called lattice easy, which is just evolving scalar fields on a lattice in an expanding universe. And finally, the code which included gravity, but non-relativistic gravity, that was a Schrodinger-Poisson code that was developed by my collaborator, Philip Motz, for fuzzy dark matter. And that was the code that we used to do that. So there are lots of different things that were done because different types of codes were better suited to do the types of problems we were interested in.
And yeah, that's good. There was one more question that, Vivian, I want you to talk. So I'm giving you a voice. Can you ask your question?
Yeah, of course. Yeah, thank you, Mustafa. Yeah, I guess kind of in regards to your final discussion about these collisions, the soliton collisions and the black hole mergers, is there a degeneracy that would exist kind of between, or like if you had different black hole masses, would you be able to distinguish between kind of this enhanced signal from the soliton collisions? Do you have any idea about that?
I was hoping somebody would ask that question, and thank you for doing so. So this is an excellent question, and we did think about this. What I'm about to say is a little bit speculative because we haven't actually done the numerical simulations with the inspirals. So keep that in mind, but let me give you the reason why we think the degeneracy can be broken. Okay, so when these objects are far, let's imagine an inspiral situation with black holes as well as with these objects. When two black holes with the same mass as these guys are spiraling into each other, then far away they should have the same gravitational waveform because they're just point particles. Nothing is changing. Okay? However, when they merge together, we will find that the signal that you get in the chirp signal that you get seems to be higher. So the signal before they merge would tell you something about the chirp mass already. But over here, but then when they merge, we expect the signal to be higher in the merger of these solitonic configurations than we expect in terms of those mass black holes. So there is a sense in which you can break the degeneracy if you had access to both the early waveform before they merged, as well as this chirp that you had. I think it's possible to break the degeneracy because it's not precisely the ring down that you would get if you just had this with black holes. Does that sort of answer the question?
Yeah, absolutely. Thank you.
So there is a possibility, but this is me speaking without actually doing a detailed template to make sure that this actually comes about. But that's our expectation.
Cool. Thank you.
Okay, I think that concludes the questions. So let me thank Mustafa again for a wonderful talk and presentation. Thank you. And